if you look at this diagram here, you will notice that it looks like an electronic circuit board, and it looks extremely complicated. And in fact, it is just a few of the cellular and molecular processes that go on in a normal cell every day. And I put this up so that you can understand why COVID-19 is very difficult to find drugs for. And in general, any disease is difficult to find drugs for, because we're dealing with a very, very complicated system. And this is just a single cell. So in fact, I'm showing you the metabolic pathways of the cell on the left and some of the pathways that are involved in cancer on the right. And it has been estimated that the cell, which is a thermodynamic analog and stochastic supercomputer, what does that mean? It means that it's a computer that doesn't just work with ones and zeros like digital computers, but in fact has events that are probabilistic, leading to shades of gray, analog and probabilistic computation. And that noisy, unreliable computation is what is used in the cell to compute. So a normal cell has about 25,000 linked state variables. And what that means is these are many of the protein coding genes and other control genes, the DNA that makes up the cell. And if you look at the trillion reaction diffusion equations that happen every second, it's been estimated that even on a powerful computer, it would take 12 years to faithfully simulate all of these trillions of chemical reactions for just 20 minutes of a bacteria's stochastic cell cycle. That means basically a bacteria going from birth to death. It would take 20 minutes before it divides. It would take that long. So you can appreciate why this is quite amazing. And the cell is also a very, very energy efficient computer. In fact, it does its entire computation in 1 picowatt of power. It's the most energy efficient technology in the world. The reason this actually matters for medicine is that the mitochondria, which is the powerhouse of the cell that is needed to provide the energy for the cell to do all of its functioning, is in fact hijacked in part in its coordination by the COVID-19 virus. And the small copy numbers of a virus, which is just 1 or 2 viruses that are entering that eventually are going to explode and take over the whole system, means that small noisy events can get amplified. And at the point where they get amplified to get a massive positive feedback loop infection, and the massive positive feedback loop causes the immune system to go into what is known as a cytokine storm, which you may have read about on the news. That is the immune system getting very defensive about what is going on. You are extremely sensitive to this noise. So the energy, the information, and the noise are all very deeply connected. And they're connected not only in cancer, but in COVID-19, it turns out it's critical. And many of the drugs, therefore, that some of which I will discuss, do address this, including drugs in cancer. It's been estimated that one cell's connectome, and what that means is how a cell connects these molecules that are forming a network to connect to other molecules in the network, rivals the complexity of an insect brain. So what I wanted you to appreciate by looking at these pictures is how complicated just a single cell is. And we have 37 trillion of them in an adult body. And so medicine is therefore very difficult. And that is one of the reasons that even though COVID-19 is moving at breakneck speed compared with many other medical diseases in terms of a cure or a cocktail or a vaccine, it is still very difficult. So I'm going to take a very quick tour that will go into a lot of detail in pictures, but there simply isn't enough time for you to digest this much detail, and it's not important that you do. I'm just going to give you the big picture, pay attention to the big picture, and pay attention to my pointer. My pointer will go in different places and I will guide you through it, and listen more to my audio and use the visuals as a prop so that you understand what my audio is saying. But I wanted to give you the whole truth and nothing but the truth, which is why I'm giving you all the visual detail and telling you what the hardcore science is. But I will also guide you through it so you don't have to understand all of this, since I realize some of you do not have science backgrounds. So the SARS-CoV-2 virus has 29 state variables. Effectively, these are the ORFs, or genes, so to speak. In this case, it's an RNA genome. So DNA is typically transcribed into RNA, which is then made into proteins. And if you look at the virus here, you may have heard of this spike protein. That's why it's called a coronavirus. It's like the crown on, it's these spiky things, and many drugs and antibodies, as well as other things, are trying to affect this S protein here. There's also the N protein, which is very important, that covers up its RNA genome, its brain, so to speak. That's the thing that you see in red there that's covering it up. And it also has this M protein, which is a protein that it uses to fight the immune system and do other things with in its envelope. And a few copies of this envelope protein, E, which is also very important. And so essentially what this virus is going to do, as you'll see, is it's going to enter the cell, and then it's going to make many copies of itself, including its brain, the RNA brain there, and these body parts, of which there are 4 primarily. And you'll see here that it also has a bunch of other small proteins that it makes to fight the immune system and continue its functions. And so this is known as the full genomic RNA of the virus, and these are the subgenomic RNAs that go into the SARS-CoV. And I've shown many of the functions on the right-hand side, and I'll be talking about some of them in the talk, so you don't have to understand them. But basically, there are what are known as non-structural proteins, as well as structural proteins like the S, E, M, and N. And the non-structural ones have many functions, like fighting the immune system and helping the virus hide when it replicates so the immune system can't detect it. And these are the proteins that kind of are its body and coat that allow it to enter cells and leave. And so we will see all of that as we move along. So I have summarized this in about 9 steps, and you've probably read about many of these in the news, and you don't really need to understand all the details, but do get the big picture. And the big picture is that it enters here, this S protein binds to a very important receptor known as ACE2. You may have heard that this is involved in blood pressure, and many of the pathologies that happen in the lung of COVID patients are happening because of this ACE2 receptor. So what happens is that it binds, it enters the cell, and when it binds and enters the cell, it basically then releases its nasty package. And the nasty package is first its full RNA genome brain, which is made into 2 gigantic polyproteins, as they're called, and it actually uses the host machinery to make these proteins. So it's basically coming in like a Trojan horse, unloading its cargo, hijacking the host machinery to make these proteins. And in fact, in the Trojan horse cargo are these proteins that will chop up the big polyproteins that are made, 1A and 1B. And these are the NSP3 and NSP5 non-structural proteins. They're called proteases because they're like scissors. They cut it up into smaller pieces. And when it cuts up into smaller pieces, then what happens is it makes this important replicase transcriptase complex. This is what is going to allow the virus to replicate. This complex assembles and makes the subgenomic body parts, and it very cleverly goes in and hides in something called a double membrane vesicle. And this double membrane vesicle is what allows it to stay hidden from the immune system for a little bit, because it's literally in the noise in the beginning, just one copy number. And in the beginning, the immune system may not notice it. And if it's hidden, it's going to be even less likely to be noticed if it's not on red alert. So then what happens is it translates these proteins, and they go through the endoplasmic reticulum, which in fact is closely connected to the mitochondria. And that's another protein that is hijacked by the virus cleverly and used. It forms this complex, the virus reassembles, and bam, it's out the cell. And if it makes many copies of itself and the immune system does not detect it in time, then what will happen is that many more of these copies will go and infect another cell, enter another cell through the ACE2 receptor, and slowly start infecting many, many cells, primarily in the lung epithelium. Now, the immune system is not stupid. It has evolved over many, many, many billions of years to be quite smart. And you and I are literally alive today because it's seen and fought in many of these wars before. Even though some of them have led to death. And so what the immune system does is it's got its own RNA, foreign RNA recognition receptors, like in this case, TLR3 and 7. It's got MDA5 and RIG1, these proteins. Note that they talk to the mitochondria, which is the powerhouse of the cell. The immune system basically now recognizes that this does not look right. We are seeing RNA that doesn't look like its host RNA and it's foreign RNA. And it goes through then a circuit pathway. And this circuit pathway then leads to two big alarm signals. The first alarm signal is sort of like the police alarm, where it says, oh, I am now going to get a whole bunch of red alert things going on that are going to allow me to fight these viruses. And that is this IRF3 interferon pathway. The interferon pathway is basically an antiviral pathway in this case, as I'm focusing on, which will let it fight the virus and create all of these proteins and other things to detect it better and knock down its RNA and make special proteases so that, in fact, the virus can get chopped up and its proteins can be examined by other components of the immune system. So that is basically what I would call the local police pathway. But then another thing that happens, which is that the innate immune system then sends out an alarm signal, and these are the cytokines, IL-1, IL-6, many others, TNF-alpha, which is basically now an alert, alerting neighboring cells' innate immune systems to be on alert. And these signals are also then sensed by other cells in the immune system, like macrophages and neutrophils, and they then come in to help. And eventually that help signal will be conveyed through dendritic cells and others for the colonels and sergeants, the T's and B cells, to come in and help as well. So you kind of raise the alarm, you get ready to fight. And if you raise the alarm and the fight becomes very deadly, what will happen is the military that comes in later on will actually hurt you and kill you in an autoimmune reaction. So you do have to be careful when you raise this alarm, which is why this is one of the most regulated and carefully regulated molecules, NF-kappa B, as well as this IRF pathway. So you say, wow, this all looks like it's pretty complicated, and it is. How are we going to find a drug, and how are we going to do this in a principled way, and how are we not going to just try a bunch of hacks on a bunch of cells and see what works, that maybe it works on some patient, maybe it doesn't work on others? Well, what are we going to do? Luckily for us, and as I've hinted, many of these biological circuits basically look like electronic circuits, and over about 12 to 25 years, I figured out how to take literally any circuit in biology, whether it's the brain, the heart, the vocal tract, the ear, the cell, even quantum atoms, and map them into these analog circuits so that basically the very complicated, nonlinear, asynchronous, noisy equations can be mapped into equivalent electrical circuits. And if you do that, then basically the fluxes of molecules become currents, and the concentrations of molecules become voltages. And the regulation that you saw of all these molecules connecting to each other results in these wiring diagrams of things where voltages control currents, and those currents go and create other voltages that create other currents. And there are many, many complex feedback loops that get built up when you wire these circuits together. But when you have done so, you have an exact representation of what the virus is trying to do and what the immune system is trying to do and how this fight will go on. So you'll see, for example, that if I take this circuit, I can make it look like that. And you say, voila, how did that happen? And in fact, why is this any better than the other one? Well, you notice here that we've cleanly separated the viral red and brown proteins in RNA, but now we've added small molecules and drugs so that we can now attack the virus at certain places in its circuit. And we've represented the fight. In this particular case, the viral replication diagram that I've shown you is being represented. And these multiplier blocks that correspond to molecular binding, these stop signs that correspond to drugs that are blocking them, these blue things that correspond to DNA being controlled to make something, including ACE2, can all be represented. So obviously this takes a lot of work to do, but once it's done, you sort of have a map now of what you can go after and how you can go after it in a principled way. And you'll notice already here that there are some drugs that you may have read about on the news that are being represented, like remdesivir and others. So if you now look at the innate immune system and you add the circuits that correspond to it, that's now shown on the right-hand side. And you can see that now there are things that might help block the immune system. Some drugs as well that are there. And these antiviral drugs, immune drugs, some drugs actually go across both. All of these, along with the wiring diagram, can be represented in an electronic circuit, an analog circuit. Now, if you do that, what are the advantages? There are 4 advantages rather than drawing a graphical hairball mathematical diagram where everything connects to everything and you have no idea what it's doing. And it is that electrical engineers who've designed circuits for almost 100 years know that the things that matter are the feedback loops, which are the products of sometimes many, many, many parameters. But the only thing that matters might be one, what is known as feedback loop gain. For example, in the cytokine response, the only thing that matters is if one positive feedback loop gain goes greater than 1. And if it does, the cell is going to go crazy and start an immune response. And if that is less than 1, it will not go crazy. So many things basically can be represented with far fewer parameters because we, A, don't know many of them, and we don't care. It is, in fact, these feedback loop parameters that we care about. There are also many, many forms of analysis that engineers have used to design complex systems that have been vetted by over 100 years of design. And those can be used automatically because they're built into the software, like sensitivity, robustness, dynamic response, noise. Another very important feature is that you can use these tools, which have been meant for design, to do hierarchy, abstraction, and modeling. So you can have a very simple level 1 model or a very complicated level 27 model that puts in a lot of detail, and decide what it is that matters, that actually fits the data. And can we get away with doing something very simply, or do we need the whole complexity? And the most important one, perhaps, is the last one, which is that physical constraints of energy. Well, it's literally the voltage times the current. Cell and molecular number, it's the voltage. The variability, it's the noise. The maximum molecular flux, it's the maximum current. The robustness, it's the return ratio. The drug dosage, it's the voltage. Literally, you'll see later on when we do hardware, we don't even have to fake temperature. Temperature will represent itself in the hardware as the temperature in the room, like it does in the biological cell. And so many things that are entangled in physical systems don't get faked in the mathematics, but are represented as an exact physical analog system with all of the complexity. So if you now take such a system, you can, for example, put in a drug cocktail. One drug cocktail with the nucleoside analog might be remdesivir, which is preventing viral replication. Another might be PB28, which is blocking a particular molecule in the virus, and SP6 from doing bad things. And you can see that the combination is leading to a better scenario where we're reducing the number of viral particles, the number of RNA, the number of N proteins, and the replicase transcriptase complex that we see. So you could say, why do we stop there? What about the full immune system? I've just shown you the virus and the innate immune system. After all, things are much more complicated. The lung pathology that you may have heard about that is causing blood and fluid in the lung, and immune cells and dead cells to invade the lung, which is leading to low oxygen and eventually killing patients, actually is involving many other things. So yes, that is absolutely correct. And I'm showing you a simple model of how you would add that. These are just some of the important molecules. There are many others. But in big picture, once the cytokine storm hits, you're going to get neutrophils and macrophages to invade. They're going to secrete chemokines, CCL2. Well, that's going to attract even more macrophages like sharks that are going to come in. The neutrophil dogs will go away a little bit, but the sharks will now cause some damage. When you cause some damage, IL-8 will be secreted. Other immune cells will come in. Eventually, the kernels, the T cells, will arrive. The kernels that come in sort of two varieties, the CD8s and the CD4s. And these CD4s that you can see will basically coordinate things, and the CD8s can actually kill cells themselves and release molecules. And you'll see here, for example, that this will then recruit B cells to make antibodies. And these antibodies are basically molecules that will go and bind up particular antigen areas in the virus so that the virus is not even allowed to enter the cell. It's basically decoyed away, so we don't even have to fight it. It's like we will not let the burglar in the door. And the coordination between the kernels and the sergeants and all the other cells that you see, the sharks, the dogs, the horse messenger dendritic cells, all will then lead to a coordinated response with the adaptive immune system, where we're making specialized antibodies now to detect certain things in the burglar. And if we're lucky and the innate immune system reacts fast enough and recruits the adaptive immune system fast enough to make these antibodies, there may be no problem at all. And you may be asymptomatic. It may just look like a common cold. You've detected it, you've made the antibodies, you've decoyed it, no big deal, you're done. But if you fall behind and you don't detect it and the virus grows in area, or you have a weak innate immune system, and the adaptive immune system arrives too late, and it's not successful in making neutralizing antibodies that fast enough or that are successful enough, you might get into a very severe cytokine storm where actually now the immune system causes death. And so once again, we can model a circuit pathway to represent that. And that circuit pathway then that represents that can come together to show us important viral proteins, drugs that we can target, and how we can go after it. So for example, if we now take this, we can now add in a cocktail that has anti-immune drugs as well, and decoy drugs as well, like the antibodies, so that the viral load can start to go down, and later in the stages of the infection, you can add drugs that calm the immune system down and prevent it from going into a cytokine storm, so that even though the cytokines are going up, eventually they will come back down and not lead to creating very much damage. And so this is showing you an example of a 4-drug cocktail. And don't get too hung up on the exact drugs that I've used, because I can give you 3 other drugs for just about each of these functions. What is important to remember is what I call the key elements of a COVID-19 drug cocktail. And I believe that there's actually 4 of them. The first one must block viral replication. This is going to be much more important in the beginning in an early stage infection than at the end where it may not matter. So this is an example of remdesivir, but it could be other nucleoside analogs like ribavirin. It could be other things that are being explored like EIDD 2801. There are many, many things that drugs that could do this. You also want drugs that block viral entry. Well, these are the decoy things that I've told you about. They could be things like APN01, or they could be antibodies that are from convalescent plasma, or they could be specially designed antibodies. But this is preventing the burglars from getting in the door, and this is making sure that once the burglars get in, they are not replicating. Both of these classes are going to be more important in the beginning than in the end. And a third one, which is sort of important in the moderate stage, I would say, but also in the beginning and even in the end, is that there are certain key things that can help the immune system fight the virus and really prevent the virus from blocking the immune system. And I've shown you an example. PB28 is one example, but there could be other things that block NSP3 in the virus, or NSP5, which is actually an AIDS drug. And many times you have to be careful because people have tried an AIDS drug in the beginning and said, oh, it doesn't work at all for serious patients. But then they tried it on early stage patients, combined it with a cocktail, and they got good results because the cocktail was well designed. And that is why the cocktail is very important. You have to hit it at many points. And finally, at the very late stages of the infection, you may have read on the news yesterday that drugs that calm the immune system, like dexamethasone, which is sort of in some ways a dangerous drug, because if you calm the immune system too much, you can get secondary infections. And if you have comorbidities, other things can happen. But if the immune system has gone on overdrive so much that now the only thing to do is to prevent yourself from killing yourself, then yes, that could be a drug that you might want to try. I showed you another example, tocilizumab. There are many other drugs that are being explored, like acalabrutinib and calcunix and other things. So the timing, the dosage, and the synergy are key. And all of these come in because you look at the whole system rather than just looking at a part of it, so you understand how it all works together, which is what circuits are about. So you may say, I've shown you some of the complexity of the virus, some of the complexity of the innate system, some of the complexity of the adaptive immune system. Where do we stop? We know there are probably 1.5 million perhaps unknown viruses, and coronaviruses, maybe in bats alone, they may be another 5,000. And as time goes on, there are going to be more pandemics. There are going to be more diseases. We've already had 3 in very close succession from 2003 to now. How do we actually think about quickly finding a cure to any disease or any pandemic that doesn't require us to kill a lot of animals and or humans? And so I want to show you a little bit about the full complexity and what that might involve if you really wanted to do this right. You might need to represent 27 cytokine concentrations. These are the stop and go molecules. So I gave you examples of IL-1 and IL-6, which are the inflammatory ones, but there are many, many other ones like IL-8, IL-2, IL-4. You saw some of them on their diagrams, but they all coordinate in a way to do clever coordination of the army to make sure that it doesn't go autoimmune, and also that it recognizes pathogens quickly on the other hand. There are things called chemokines. If these are the what signals and the control signals, these are the where signals. And they say, aha, there's damage in the lung. IL-8 is secreted by a fibroblast. Immediately a neutrophil might enter and say, I think there's some damage here. I'm going to come in and sound an alarm, and I'm going to start doing things involving the blood and clotting and healing that will cause a wound healing response or recruit other things in the immune system to it. And they have very incredible combinatorial complexity when they work together. There are 12 toll-like receptors. These are receptors that detect, for example, single-stranded RNA, double-stranded RNA, the tails of bacteria on them, called flagellins, or maybe the membranes of bacteria on them, or double-stranded DNA that looks foreign. All of these things, along with their ligands, all compose the immune system. There are many, many types of immune cells, and they could be divided into about roughly 8 classes, give or take. And the numbers of B cells, T cells, macrophages, neutrophils, all these cells that work together have to be represented. You would need the pathogen copy numbers. In the beginning, the virus is in the noise. There's just one of it, or maybe 10 of it. And later on, it's all over the body. And so the state of what you're going to doing has to be represented. And what you've seen from just yesterday is that it's quite complex. Hormones like cortisol that regulate the immune system from morning to night and overall shut it off or turn it on are very important, like dexamethasone can block them. So you need hormones, the hypothalamic state. Men and women are different. The permeability of the vasculature, very, very important in COVID-19. And inflammation often causes redness, swelling, heat, and pain. That has to do with the fact that the vasculature is getting more permeable or less permeable, depending on what is going on. The nervous system actually, through the vagal nerve, modulates the immune system. That's being explored in arthritis. There are many, many things that have side effects that affect the immune system, that affect the nervous system as well. And you've seen the lung pathology and comorbidities that affect a disease. Energy and metabolism are key in COVID-19. They are key in many, many diseases like cancer and diabetes as well. And so a drug cocktail has to take all this into account, including safety, efficacy, side effects, site of actions, adaptations to symptoms in patients, depending on whether they're late or early. So you might say, this is hopeless. We will never be able to cure an arbitrary disease or an arbitrary pandemic. We're going to have to repeat this level of death again. And I don't think so. I think we should be prepared next time, and we should take both an empiricist and a rational approach. I'm going to focus on the rational one. The question is, how do you take this, and this doesn't even represent the full complexity, and build a supercomputer that can actually represent this complexity and give us intelligent drugs and drug cocktails that can handle this? And the answer lies in the fact that you have to combine physics, chemistry, and biology. And fortunately for us, the same laws of physics and thermodynamics that affect chemistry also affect electronics. So there's a way to actually take the trillions of chemical reactions and map them into very efficient electronic circuits that represent them exactly. And what that means is that in a chemical reaction, as you go from a reactant to a product, you're basically climbing up an energy hill and going back down. And the product will simultaneously go back into a reactant, but it's less likely because it has to climb a bigger hill back. And the difference between the number that climbed the hill this way and the number that climbed the energy hill that way is the net molecular flux of the reaction. And enzymes are these very clever molecules that improve the rate of both the forward and backward fluxes. And the stochastics, which is the noise of these asynchronous processes going forward and back, the sum of the two is the Poisson noise. So if you look at how electrons flow in a transistor, and these are basically the same transistors you see in your computer all the time or your cell phone. You have millions and billions of them in just about every device you are now using, including the one I am. These transistors that compose integrated circuits actually have electron flows in them. And there, an electron goes from a source terminal to a gate terminal, which, because you control the voltages, you change the energy levels in effect programmably, rather than by configuration of the molecule. So you get a forward electron current and a backward electron current. And the difference between the two is the net electron current, like the net molecular flux. And just like enzymes can lower this energy barrier, a gate voltage can lower the energy barrier and speed up the reaction. Here, basically speed up the electron flux going forward or backward. And so what happens is that the sum of the two fluxes then gives you the noise. And what that then means when you're all done is you can take circuits that are biological that look like this. In this case, I'm showing you what happens in certain biological circuits where the DNA is coded into RNA and into translation, make them into very exact mathematically equivalent linear, nonlinear circuits that represent them exactly. And like Lego blocks, you can then combine these circuits to do arbitrary things that you might want to do. So I'm showing you actually about 8 different Lego blocks that are very important in genetic circuits, but these allow you to basically model the complexity of many of the things that I showed you in the immune system and in the viral pathways. Now you can take these and you can also model arbitrary chemical reactions, which literally then allow you to do anything. And when I mean anything, I mean literally anything in the cell. And that means you can do fan-out pathways, fan-in pathways, feedback loops, where things break apart, where things come together, where things dimerize, where things break away. And you can then simulate them by changing the wiring diagram in software and changing the parameters also in software so that they change the values of analog currents. So as an example, I'm showing you an example of the p53 cancer pathway. This is a very important pathway where small copy numbers of this p53 molecule can determine whether the cell is going to commit suicide or not. And in a lot of cancers, the committing of suicide is actually what saves you. And so you can see here that that can be modeled exactly. But the same idea is also true of COVID-19. We just have to change the program and the wiring to represent what I showed you before rather than the p53. So it takes a lot of very serious engineering skill to build these analog circuits, unlike digital circuits, which could be done in 8th grade if you know how to do logic. These involve a lot of feedback loops, noise, design, and you have to get things to work. But when you're all done and you get your PhD, you actually can design very efficient circuits that are digitally programmable that can represent these computations. And perhaps one of the most important things is that they can represent them exactly. And not only can they represent them exactly, they can naturally use the noise by emulating randomness with randomness. And as I told you, this is very, very important in biology because it's very difficult to do random pseudonumber generators and do them asynchronously. And Google's quantum supremacy processor also leveraged the same power of quantum computing to allow you to do analog wave interference and analog randomness in order to solve and search for things that would be very hard to do digitally. In fact, you can show digitally that you cannot, if you have an arbitrarily large network and an arbitrarily number of molecules, parallelize it. The time keeps going up and up and up and up and up and up, cubically in the number of molecules or reactions. Whereas in an analog system that is truly asynchronous, you can build a parallelizable system that is flat in its scaling. And that means that you can get massive speed ups when you scale up such supercomputers. For example, if you got a 7 million speed up, something that took 12 years to do could be done in a minute. So if you take something that takes 12 years to do and you can do it in a minute, you can try many, many combinations of drugs, drug cocktails, parameters, things that you don't know, and say, which are the ones that actually will fit the data? But this is not enough because you don't want to be hand coding this. You really want to compile the thousands of models that we already know that describe biology into these chips in the same way that we write code in a high-level language like Java or C and compile it into machine code that runs on the Intel chips. And in a sense, what I've told you is how you build BioIntel chips that are digital inside and outside, but are analog inside, and you need a high-level language, and that language that a lot of people use is called systems biology markup language. And so I collaborate with people who write such compilers and are computational biologists who can actually compile such complex models so we don't have to hand code them. We are hand coding some of them manually for COVID-19, but in the future, if you have to scale it up, this compiler has to get written so you can try things quickly. And you will eventually have to do this hardware, supercomputing hardware, in such a way that you learn and fit data. And this is important because there are many parameters that you don't know. You don't want to overfit the data. You want to do it with as few parameters as you need, every one of which is biologically derived, and some other ones that you might know from literature and measurements in chemistry and other things. So you want to do experiments on cells, for example, try drugs on them, see which ones kill the virus or not, figure out what is consistent with what you're seeing based on the viral proteins and the host proteins, map them to the cytomorphic hardware, check to see what is going on, and quickly suggest new drug cocktails or improve your models to explain what is going on so you can get there. And so I've given you a vision of how this can happen. And in my lab, we've built prototypes for how to do this. They're not a full supercomputer yet, but you can see that you can take these cytomorphic chips and put them on boards to build small scale versions. And my student, Doug Beam, recently, in fact, at breakneck speed, got some drug cocktails to already work on them. And you can see, for example, that the software results that I showed you earlier can now be replicated in hardware as well. So when you're all done with these simulations and drug cocktails, there's some big picture things that emerge about every disease that are quite important. And so I want to talk about one of them. And that's because this is showing up in COVID-19 over and over again, and is actually a common issue that shows up in just about every disease. And this is a fundamental engineering trade-off in an immune system that comes from engineering, where it simply cannot be perfect. There's going to be noise within a cell, there are going to be errors, there's going to be noise outside the cell. The past pathogens of the immune system are going to set a thrust threshold. It might say, that just looks like something I've seen before, that's not a virus, that's just normal fluctuation. But if it's seen many past pathogens before, like many past coronaviruses, it might go, whoa, 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 that looks really weird. I don't like the look of that. And I'm now going to examine that very carefully. So there's certainly a cost to doing that. And if you spend all your time examining every small little thing that looks abnormal, that's all you'll be doing. But on the other hand, if you do not pay attention to the things that look abnormal, you could die. So it's a robustness efficiency trade-off, a universal trade-off in engineering that shows up in just about every domain. And so engineers have come up with something known as a receiver operating curve. It's just sort of like a thrust threshold. If you set the threshold too high, you have too little trust and or tolerance for error, you're going to get a lot of false positives. Things that are testing like, oh, that looks like a pathogen, but you're actually going autoimmune and you're going to start killing yourself. On the other hand, if your threshold is set in a way where you're not paying enough attention, it's set too high, the virus will go undetected and replicate into hundreds of copies before you detect it. And the infection will grow, and then it'll be too late because you will be then like the speed limit. You'll have to catch up and deal with that. You'll have to run really fast. And if you run that fast, you're going to exceed the speed limit and could burn and kill yourself. And so these trade-offs are very, very key. And I want to now tell you how these trade-offs actually affect the drug cocktails and how we plan to take them along with what I've told you to make this actually practical in the future. But first, I want to acknowledge all the people who've done the work. The two key people are Douglas Beam and Dr. Yiji Deng. Doug did a lot of the analog circuit and cytomorphic chips, and Dr. Deng is a master biologist who works with him on the pathways as well as an experimental biologist, and together they have done most of the work that you've seen here. John Thayer did a lot of the work involved in mapping biological circuits to electronic circuits, And Tanner Riley, an undergraduate, was responsible for many of the beautiful diagrams and a lot of the work involved in finding parameters and the models and the biology that went into the circuits. My collaborators at the University of Washington who write the compilers are Herb Saro and his student Kyle Medley, who just graduated. We are now collaborating on revision 4 of the cytomorphic chips with another professor, Samijit Mandal, and his graduate student Haishang Zhao, who are working with us for the future versions of the board that you saw. And we are also collaborating with lead computational biologists as well as experimental biologists. This is Nevin Krogan at UCSF, one of the world leaders in finding drugs and drug cocktails. His approach uses chemoinformatics and proteomics, and basically works on vero cells and infected lung cells. And there's also a pipeline to the Mount Sinai School of Medicine. So if we suggest any cocktails to him, he can try them in his cells and eventually they can get to patients. And Nady Bahudi and Ben Polico work with Nevin Krogan and us so that some of the things that we work on can eventually get to patients. And I should finally also acknowledge Dave Shenoy at the Information Sciences Institute at USC. He has helped define what it would take to actually scale this to make the tens of thousands to hundreds of thousands of VLSI chips that might take to actually build the supercomputer someday in the future. And USC and ISI actually specialize in doing this. And I also want to mention useful discussions with many people at Dartmouth that have helped this project. So let me summarize many of the things that I've talked about. And I want to leave you with 6 things, and then I've got some time for questions. First, I've shown you how you can rigorously take biological circuits and map them into analog circuits that are useful for getting drug cocktails. Second, I've shown you that there are 4 key elements of a drug cocktail. Third, I've shown you that there are fundamental engineering trade-offs that have to do with autoimmunity versus pathogen tolerance. Fourth, I've told you that it is taking very long to find treatments in COVID-19 that work. In fact, it's going at breakneck speed, but you are correct to be frustrated that this is not scalable and we would like to do better. Unfortunately, we cannot do better on simple digital computers because biology is very, very complex. But fortunately, if we take a mixed signal approach that combines the best of the analog and the digital worlds and leverages the connections between chemistry and electronics, we can build cytomorphic computers that can help us for pandemics in the future, as well as for COVID-19 drug cocktails now. And so I'm going to end here now and open the floor for questions. So Jennifer, do you want to perhaps repeat them to me and I will try and answer them?
Sure, yes, thank you very much. This was a wonderful presentation with lots of information, and we did receive some questions in advance from our registrants, and so I have a couple of those, and then I encourage for those of you who are on to click on the Q&A button at the bottom of your screen and submit your questions live, and we'll go through some of those. So just to get us started and kick us off, we did have some interest in knowing if these supercomputers could possibly be adaptable to diseases characterized by dysfunctions like diabetes or cancer. And then with that, maybe even, could they even model neurological processes and mental diseases as well? Thoughts on that?
Yes, absolutely. In fact, as I've shown you with these pathways, we already have done P53 for cancer. But in the end, the thing that changes is basically what these biological pathways are and how we map them to the hardware. But just like you can write any software program to do anything on a computer, you can model any disease by changing the wiring, connectivity, and parameters. Next question.
Marco has asked us, conceptually, could this approach model neurons, synapses, and ultimately consciousness?
Oh, Jesus. Okay. All right. It certainly can model neurons and synapses. That's no big deal. That was actually pioneered in 1985 onwards by my own advisor, Carver Mead, and many others now, and is, what deep neural networks and other things are about. In terms of modeling consciousness, Christoph Koch, as you might know, is one of the pioneers on it, and he believes that there are certain key feedback loops and certain critical numbers of neurons that are needed for you to say, well, an insect isn't conscious or a virus isn't conscious, but we are. And in some sense, it's about being aware of things beyond ourselves and having an awareness of ourselves as part of a bigger whole. So I do think that those are emergent properties that can emerge in certain systems, and you don't even have to invent anything flaky about it. It will just come in the system, because once it gets aware, it will realize that there's a benefit to understanding that I'm just part of a bigger whole. So yes, I think the answer to that is yes. Next question.
How will quantum computing fit in the future? So thinking about as we move into the future, what is the role for quantum computing?
Yes, so as I've already indicated, quantum computing leverages a lot of analog wave interference and randomness to do very interesting search and find solutions to things that are very hard to do on digital computers. But in fact, in this particular project, it is also very useful in finding drugs. For example, enzymes are the masters of quantum chemistry. And you can do a lot of drug design by trying to see if we can, from first principles, do quantum chemistry drug design. So I believe quantum mechanics will be very, very useful, not just for factoring numbers and things like that, but also quantum chemistry. Next question.
Great. A question coming in live is about validating the results of your cytomorphic supercomputer. So how will you go about that on drug cocktails in biological systems?
Very good question. So as I told you, we have a collaboration with Nevin Krogan, and there's a sort of three-part step to it. First, you've got to try those on cells like lung cells or HEK cells or Vero cells are very popular now. And then if that works, then you try them on animals. And then if that works, you then try them actually on humans. And you have to go through that pipeline for reasons of safety. I've actually tried to directly contact doctors and say, here's the cocktail, why don't you do compassionate use? And they always push back and say, yeah, well, that's very well fine, but that'll have to go through an IRB. And in fact, one of my cocktails that I predicted could have been tried and was tried in a slightly different form. But unless it's a compassionate use case, you have to go through cells, animals, and then humans. Next question.
There was recently a paper published on the same research line by a group in Israel using memristors. Are there any advantages or disadvantages in using memristors for building cytomorphic supercomputer instead of bio-CMOS technology?
Yeah, memristors are basically a technology that allow you to remember things. So they have an advantage in that the analog memory, which in this case is being done digitally in the version that I showed you, can be done more compactly. But one of the disadvantages of memrisistors is they have a finite number of cycles. So if you, for example, learn 100,000 times, you might destroy them because of the physics of the device. Whereas a digital computer can be, programmed infinite numbers of times. So if you're storing the bits digitally and the parameters digitally, there are some advantages to it. I think in the end, it boils down to whether you're doing the analog memory efficiently and what some of the pros and cons are. And memristors are, of course, also a relatively new technology that is untried. Most of what I've talked to you about could be done on VLSI chips that have existed for a long time. The innovation lies in the circuits and the hardware. Next question.
If quantum computing ever gets up to par, could you then begin to preemptively develop drugs for diseases not seen yet?
Very interesting question. Yes, if you actually go do a three-part analysis. First, you'd have to look at the pathways of the whole human body. and say, okay, how could they go wrong? That would actually be sort of a robustness analysis. Then from that, you could say, what are the 4 molecules that could fix them? And then you go to the quantum computer and say, how do I design these 4 molecules? Because they're based on drugs that do not exist. And you might find you have to go back to first principles to reconfiguring the atoms in such a way that you can do that. Next question.
How do you monitor side effects of cocktail drugs using your chip? For example, dosing, sequences of drugs being given.
Fantastic question. Yes, that's a very, very good question. And that is why I alluded to timing, synergy, and dosage is everything. The dosage has to be resonant with moving healthy voltages and currents so that they don't become diseased voltages and currents. So imagine that a virus infects it. The cytomorphic voltages and currents now have a diseased profile. And in a normal healthy cell, they would have, and in a cytomorphic chip emulation of them, a healthy voltage and current profile. So you actually have to learn to make sure that the dosage is such that the vector treatment of the drug cocktail is moving you in the right direction. And in fact, that's what allows us to do the machine learning in a clever way as well, is that you can borrow from many of the learning algorithms that have done similar things in other domains. The timing, as you have asked, is also very critical. A drug cocktail that is important in the beginning might be terrible at the end or not efficacious at the end, and vice versa. And so you must adapt to the symptoms. In my opinion, smart drugs of the future will do 6 things. They will A, be a cocktail. B, they will go to the site of action automatically. 3, they will adapt to symptoms automatically. 4, they will automatically minimize side effects. 5, they will automatically be safe. 6, they will automatically be efficacious. That is the power, I think, later on of actually using live drugs that we might engineer like people have done in CAR T cells, but maybe in the future we could have CAR NK cells or other cells, smart immune cells that are customized with synthetic biology and feedback loops in them to do this. Next question.
Great. We have, I'm going to just do one last question here as we're coming up at the end of our time here today. Question says, how does this approach distinct itself from high throughput screening commonly used by the biopharma industry?
Yes, so this approach, as you probably picked up, is computational, but is combined with the high throughput approaches when we do experiments to reduce the amount of high throughput that you need. So it's even higher throughput. In other words, rather than trying 10,000 drugs, you only try 10. And combinations of drugs are actually combinatorially explosive to try in high throughput. It's very difficult to do. And also many, many combinations of cocktails and dosages would be infeasible to do in a high throughput experimental drug pharma type approach. So our approach is complementary. It's basically going to help it by reducing those numbers of combinations. And Jen, I want to say, because we're only 3 minutes over 1 o'clock, I'm happy to stay another 20 minutes if there are a lot of questions, and those who want to leave now can leave, and we can continue with the questions, because in some ways the questions are the most fun part.
Sure, absolutely. So I do want to thank you for everyone for joining us today. And like Professor Sarpeshkar just said, if you do have to leave, we want to thank you, and please feel free to do so. This is going to be posted on our Thayer alumni website. But for those of you interested to ask some more questions, feel free to stay on. We do have several questions that came in advance that we will continue to review. So another question that came in said, should there be some sort of national COVID-19 data policy? So maybe not directly related to what your research entails, but what are your thoughts on that?
Yeah, I think there should be one which is very, very open. In other words, you share all your data with everybody because it's in the world interest to do so. And if you need to keep something proprietary, it could be your particular method of doing something that generated the data that still allows you to earn money. And I think if this is combined in an intelligent way, it will be good for all. Next question.
How do you recommend the production of vaccines can be made widely available, inexpensive, and dispersed democratically? So again, we're thinking more on the drug development side at this point.
Yeah, that's a very good question, and I think the jury is open on that. There are some people who think the cheapest way to do it will be with RNA and lipid nanoparticles. And one of the issues is that that might be good at small scale, but it's never been done before. And how are you going to refrigerate it and ship it to Africa and other tropical countries? Because the refrigeration cost is very, very high for certain vaccines. So maybe it should be manufactured there. There are other people who think that it should be done with yeast and that we should basically engineer yeast. And in fact, certain insect cells have been proposed as well. And so I think there are so many vaccines out there and so many things going on now. I think the last count was close to 1,000 plus. And as you may know, mode RNA 1273 is in phase 3 trials. So we'll have to see how it works, but it looks promising. So I think time will tell. And I do not believe anybody knows a definite answer to that because it's so different from what we've seen before. But I do think that novel solutions that do not require refrigeration will help lower costs.
A question asking, how does cryptomorphism work?
I think that might have been a typo. Maybe what was meant was cytomorphic.
Oh,
so
yes.
What I have answered, I think, is cytomorphic systems are mapping chemical reactions exactly to electronic transistor equivalents, as I went into in my whole talk. And so it works by basically doing this map and mapping equations in one domain to equations in another domain that exactly represent them. Next question.
Yeah, coming to our last question that was submitted in advance says, what is the grammar of B cells and does the immune system have a channel capacity for transmitting resistance to infection?
Yes, yes, that's a very difficult and very interesting question. I'll try and answer it as best as I can. So when the immune system is on alert and decides that now I'm going to go and find an antigen, there are these highly variable regions. There are 3 of them, and in B cells, they comprise about 110 amino acids. And so if you take about this 110 amino acid region and say, well, I could design an antigen for any of them, meaning any 20 amino acids in any position, you would get that there are about 440 bits of information in order to get that entire sequence. And if you did that in 14 days, that would give you a channel capacity of 440 bits divided by 14 days, which would look very low. But it turns out that there are about, 1 billion to 10 billion B cells working on it. So if you look at the channel capacity of the whole immune system, that could be close to 5 megabits per second in terms of finding and transmitting this. But having said that, you want to be careful because you do not remember and transmit infections and antibodies that haven't affected you much. For example, they found in COVID-19 patients that the ones who do really badly don't do well with antibodies, and the ones who hardly have symptoms don't remember them either. The ones who actually remember the antibodies are the ones who've had moderate levels of the disease. And that sort of makes sense because the ones who have been really badly affected weren't successful in making them. So what are they going to remember? And the ones who, hardly were affected by them don't see it as emotionally significant. They're not going to remember it. So it's the ones who are sort of in the moderate area who are going to remember it. So it's a complex question, but that gives you an idea of how you might think about it. Next question. If there's any new ones as well, we can keep going. Yeah, I love questions.
We just had one come in there about resources that you need. So do you have the resources you need to scale the research at an appropriate rate?
I would love to get more. Let's talk.
I thought that might be the answer.
Okay, yeah. So whoever asked that question, please email me and contact me. Okay.
Another question coming in. Can you explain how do you intend to do quantum computing at room temperature, as you had mentioned in your TED Talk? And then there's a second part of the question. When can we expect your paper on using of cytomorphic design for simulating the adaptive immune system be published of those that might be interested?
Interesting. Okay, so I'll answer both questions. The first one, the 4 patents on the quantum computing just have all been allowed. And so we are working very hard on the LSI chips as well as the algorithms to publish our first paper on them. And these circuits work at room temperature because they do classical analog circuit emulations of quantum physics. And so it turns out you can emulate all of quantum physics with 4 analog circuit parts, something I call a Planck capacitance, something I call a quantum admittance, something I call a quantum transadmittance, and a quantum transadmittance mixer. So we've now built all of these parts, and we're putting them together in systems, including quantum cochleas, quantum tensor product architectures. And so I don't think that will be that long. Perhaps you will see papers published on that in a year or 2 or 3, and many, many of them. And they work at room temperature because they're efficient classical analog circuit emulations of quantum computing, not digital. They leverage many of the same analog wave interference as well as analog stochastics that I've talked about. The question on the adaptive immune system and the cytomorphic papers, we are working as hard as we possibly can. Literally, I knew nothing about COVID-19 till mid-April or so. And in the past 4 months, I've learned everything I possibly can about it. And the science is changing so fast that a lot of what you're seeing is because Doug and Danielle worked incredibly fast and hard to make it here. And so we will slowly write this up. And we are planning to get this into many papers on the viral replication, the adaptive immune system, the innate immune system, and eventually into the cytomorphic versions of large-scale supercomputers and how to emulate them as well. I told you Rev 4 of our chip is being designed, so we may even have some results from them. Next question.
Those are all the questions that we have at this time. We can give folks just a minute or 2 to maybe ask any questions they would have, but I always like to give our professors at the end of the presentation some time just to say, leave us with a few of your reflections. Final thoughts from Professor Sarpeshkar before we end our program today. Professor?
Final thoughts. Let's see. Combine curiosity and fun and follow your heart in everything that you do, and then the rest will follow.
Excellent. Wonderful. Thank you so much for that. And thank you for spending time with us and sharing your expertise and your knowledge and your research with our alumni, Dartmouth community and students. And with that, I do want to thank all of you for joining us as well. And this does conclude our program for today. Visit thayeralumni.dartmouth.edu. Under virtual events archives, you will find the recording of this program for future playback. Again, thank you, Professor, and thank you for all of our participants today. Have a good day.
Thank you all for coming. Bye-bye.
Bye-bye.